So let's talk about a process for life cycle design. Okay, and I'm going to call this the decomposition approach. It's a simple three-step approach. It begins with understanding your design, understanding its impact, and then reducing the impacts. Sounds pretty easy, right? Let's, we're making a coffee maker. We're designing one, and we're going to understand what that design means, how it functions, what alternatives might exist. Then we're going to understand what the impact of that might be. So it could be life cycle assessment. It might be a related method. Then, we're going to try to do something to reduce that impact. So 3 steps, hopefully as intuitive as it gets. So one way, how many people have seen functional decomposition before? Oh, I know a few of you have for sure. Come on, Lisa, you were in 450. So you saw it, didn't you? I'm not going to make you define it. Functional decomposition. Sound familiar to you?
Oh, yeah.
Okay, good. All right. All right. She's so focused on tracks, trade-offs, and drawings. So this is, I'm surprised. We've got a lot of engineers here. Functional decomposition is a way of going from inputs to outputs that sort of tediously define the unit processes. So you could think of LCIA as something of a functional decomposition. The idea being, okay, I've got a function. We're going to decompose that into sub-functions. And the idea here is really generating new concepts. So if I've got a coffee maker and I need to heat water, what are all the ways I can heat water? I can have a nuclear chain reaction in my coffee maker, and this is going to solve all its problems, right? Or not. But the idea is if you break the overall flow into the sub-functions, and you can come up with ideas for the sub-functions, then you can put them all together. You get a ton of combinations, which can be evaluated. Right? So functional decomposition is useful not only for creatively coming up with new designs, but also isolating where the environmental impacts are, because these are tied to unit processes. Okay, so let's talk about a coffee maker. We've got an example for anybody who's interested. We've got a life cycle design example, reading number 17. This is the introduction to the Eco Indicator 99 method. There's also reading number 26. Both of these are optional. That talks about the end of life strategies for a coffee maker. And that one's going to come up in, a few weeks. We'll talk about that one again. Functional decomposition of a coffee maker. This is a simple one. We're thinking about coffee. We're thinking about energy, water, filters going into the system. We need to measure the water. We're going to store it. We're going to heat it. We're going to transport that heated water through coffee grounds. They're going to mix together. We need to separate out the coffee grounds. Unless you like Greek coffee, then that's a different system over there. Then you're going to store that for a little while, and then you're going to drink it. Along the way, there's some energy losses. You're going to get some more material out. That's your hot coffee. You've got a filter that's waste. You've got grounds that are waste. And anything missing? That seem reasonable? We have a lot of coffee drinkers we established in this class. Go ahead, Lisa.
So a question, how does this differ from, I guess, that first stage of our LCA where we also do the breaking down into...
Well, you might, first of all, this is a product, right? So this is a product function. It's not a life cycle, right? So that's one big difference. These are not necessarily unit processes. Like you could have, just suppose I was doing the, I had a functional unit that was serving, 1,000 customers at fast food restaurant in a, some time period, right? So coffee might be part of that, but I probably wouldn't take that to a level where I would break the coffee maker down into the functions needed, right? You could treat that coffee maker that's part of serving those customers at the fast food restaurant as a system, and I'm not going to break it down further. This is more of a design and product context, but there are similarities for sure. Other questions? Okay, does everybody understand this functional decomposition? So here's a product embodiment now. So where we're looking at, taking or disassembling a coffee maker. You've got a heating unit. You've got some plastic tubing. You've got a hot plate. You've got some fasteners. You've got, what else? The mains, the plug, say a polypropylene housing. We've got some, the glass jug and the handle, and a sort of a support strip there, band. What else? Seems to be the whole thing. So this is a product that can achieve those functions. So let's take that concept now and try to understand its impact. This is where we might do a life cycle assessment. We all know what life cycle assessment is. We've talked about it enough times. For the coffee maker now, this is a simplified set of unit processes for the coffee maker. We might have the polypropylene coming in. It's being transported to be injection molded into the housing. We might have glass that's also being transported and finally formed into the shape of a glass jug as part of this coffee maker, and etc. You've got distribution here. The use of the coffee maker, maybe it's going to be for 5 years, 2 pots of coffee a day or something like that. Make some assumptions. You've got waste coming out, and then the question at the end of life, what happens? Maybe in this case it's going to be a landfill. In other situations, maybe it's going to be disassembled or what have you. So we can now look at those stages. We can break the stages up into the unit processes. And for each of those unit processes, it's the familiar story. You got the resources coming in, you've got the waste coming out, and we can take them sort of one. How did that happen? That was pretty cool. I have no idea what's coming. I am not in control. Let's see if we can do that again. That was pretty cool. Wow. See if we can do it. Oh yeah, look at that. That's when PowerPoint has gone too far. That's the point. All right, so these are the masses of the materials. You got aluminum ingots, polypropylene, PVC. You've got polyethylene terephthalate, so bottle grade stuff going on there. Some copper, some low alloy steel, some glass. And we might, think about Eco Indicator 99. Again, not a method that we're advocating, but we're going to get into Simapro in a few minutes. And the default sort of impact method, the endpoint method that is in Simapro is Eco Indicator 99. So we'll just carry these points along. Remember that these 1 millipoint or 1 point is 1/1000th of the average European's environmental impact in a year. These are in millipoints. Just to give you a sense, we could look at energy just as well, and actually the story wouldn't be a whole lot different. So don't get hung up on the points. It's not what I'm trying to get across here. What I do want to use these slides for is just to talk about the processes. You talk about the materials, we talk about the processes, we talk about injection molding, extrusion. We might have forming for the glass pot. We've got electricity used in assembly and testing. We've got packaging. We've got foam for the packaging also, so the coffee maker doesn't break. And you get a sense on the right-hand side what some of the relative environmental impacts might be over the life cycle of this coffee pot. If you think about transportation, you've got different components coming from different places. So this was done in Europe, so we got a 230-volt cable here. We got filters, we got packaging for the filters. Again, relative environmental impacts. I will point out, it will come up again next time, that the impact is going to be related both to the distance and to the mass. So, how many tons are you moving over what distance? And that's a reasonable way to talk about the environmental impact associated with transportation. The use stage, this goes back to some of the assumptions that were made. This was a real LCA that was done, and I'm just shortcutting that to kind of talk about how do you model the system. But this is a 5-year coffee pot, twice a day, 5 cups of coffee each, and we're not recycling it. It's just a landfill. So here are the electricity demand here over the 5 years. 700 filters roughly. No, more than that. 3,600 filters. Wow, that's a lot of filters. And then they come in packages, so you've got 73 packages coming from different places. Okay, we could add up the points associated with those, and where are the impacts? Who was paying attention? What are the biggest numbers? Use phase. So if you add up the materials, the manufacturing, the use, and then the filter production, which is part of use. Chelsea?
On that last slide, or 2 slides ago, where you looked at the weight versus and the distance, are the logistics of the supply chain not really included in this?
So they are. They are. So the forward, they haven't listed everything here, but they did include the forward distribution. So you've got the coffee maker that's produced being sent to warehouses, it's stored, and then it ends up at a Target or a Kmart near you, and you go drive and get it. So they account for all that. It's just not all listed here. Okay, so what you get using the Go Indicator 99 method with millipoints, something that looks like this. If you did it with just energy, it wouldn't look very different from this. Of course, there's other things we might be concerned about other than energy, so we'll save those considerations for later. So we understand now what the impact is. To blow through an LCA. I mean, you wish you could do that as a designer, right? But this tends to be where the hang-up is. I mean, as engineers, understanding a design, not a big deal. That's what we've gone to school to do. And coming up with ideas to reduce the impact, that's we're design. That's what we do. This is the fun part, right? And usually the hang-up's in the middle, and I just blew through it in 10 minutes. But obviously then we've talked a lot about LCA and the difficulties getting data and interpreting and all that. So let's just assume that we have that information. Then we're designing for the environment. We're reducing the footprint there. Because design for environment is a term, the way it's defined, it's really life cycle design with people aspects in it. So when you talk about designing for the environment, you're talking about achieving the design performance with minimum environmental, so that would be life cycle design. But when you add health and safety to it, then it's design for the environment. So splitting hairs a little bit, but there is a difference between life cycle design and design for the environment. Environment is taken to be the broad environment that includes health and safety too. Okay, so who's going to design for us a coffee maker? You saw the design, the glass jug coffee maker. If we add up the points, 72% are in electricity, 23% are in paper. Materials are shown, so they're roughly proportional to the area of the squares. So here's distribution, here's disposal. I didn't even mention disposal, it's small. And here are the materials. So how can we design a better coffee maker? Who's got some suggestions? Go ahead, Lauren.
Use a thermos instead of like a heating plate to keep the coffee warm.
Anybody seen these aluminum insulated coffee jugs? Usually at a restaurant. Typically it costs a little bit more.
Yeah. Coffee's better too.
Coffee tastes better, no doubt the coffee tastes better. It does. Absolutely does. And why does it taste better?
It doesn't get burnt by the heat.
So it's not continuously being heated because the glass doesn't hold the heat in as well as an insulated carafe would. And so the idea with the hot plate we showed is that you have to continuously kind of heat it, and after an hour of that, it tastes nasty, pretty much. So get your coffee while it's fresh, stays fresh longer in the carafe. So that's one very nice suggestion. It's going to save a lot of energy. Vineet?
My coffee maker has a permanent filter. It's a metal wire mesh filter. Doesn't use
So
paper.
getting rid of the paper using a metal wire mesh filter. Good idea, but we're using metal, Vineet. Why aren't you concerned about that? We can,
It is.
We can regrow trees, but we can't regrow metal.
I mean, if you see the numbers there, you use metal to actually build the coffee maker itself, and it's definitely not.
Touche. Well said. Well said. Yeah, he's already noted that you're using less metal in the filter.
And the filter might use even lesser
Could be
amount
it's
of
thinner. Yeah, so you have less metal
metal
content.
than the machine itself.
So thank you for batting back my jesting. That's exactly right. So these are the two suggestions. thinking about the new filters, thinking about the energy losses, and that was the answers we were hoping that would come out. And if you actually do that, they were not paid, by the way. This is what happens to your points. Okay. Any other good ideas for coffee makers? Go ahead.
Maybe you have a solar-powered one and then you produce electricity.
Nice. So the impact of electricity would go down. Now, I tend to need coffee the most in January around here. Yeah. So it's kind of cloudy around here in January. So it depends how this is being managed, I suppose. We got plenty of wind, though, that time. So, seeing germ projects growing. Go ahead.
Do you use like a pour-over coffee, where it's just like a ceramic thing that you pour it through instead of all that plastic and metal into the actual coffee maker?
Okay, so should the ceramic style have less footprint associated with it? Now, would you have to plug that in?
You have to heat up the water, so either on your stove in a kettle, or if you got like an electronic kettle, or whatever, however you do it.
Nice. I haven't seen one of those.
Makes better coffee.
No, she's on board. She's on board. Good, Matthew?
I have a roommate who likes to load up the coffee maker from his Brita filter straight from the fridge. So he starts with really cold water. If you did something possibly like maybe not have a filter built into the coffee maker, but perhaps have one that just had a way to store the water so that people didn't want to use anything from the Brita.
Interesting. Nice. Good thinking. Go ahead.
This is more like a hypothetical idea, but if you're using electricity to heat up water, that's actually going from high-grade electricity to low-grade electricity. So instead, you could use burn a fuel. So in case you had a certain amount of fuel in the coffee maker, and you have in a gas stove, to heat up the coffee maker,
So you want to put some coal pellets?
It's a hypothetical idea. You could have some.
You have a natural gas line going to it, and you have natural gas in your house. Why not?
Ethanol.
What about the water that I use to wash the metal filter?
That was accounted for in this. So this is an excellent question. So in the analysis where they looked at the metal filter, they did look at the washer. So you got to think about that. Almost got us there. Good.
Instead of metal filter, like in Brazil they use, it's like cloth. And you
Wow.
get
Is it
rewash.
reusable?
Yeah.
And it can be reused a lot?
Yeah.
Forever? Interesting. Okay, that would probably be less. The function's the same. Nice. Okay, so you get the idea. These are things that we can be doing. And, to be clear, this is life cycle design. Now, there's some of the things that we're getting into now regarding does it taste better and therefore could we market it? Start to get into environmentally sustainable design. Does it cost too much? Is it ridiculous? When I come back to the point of dropping coal pellets into the coffee maker, well, life cycle design, that might be just fine. When we talk about environmentally sustainable design, you got to think about now the economics of the matter, the practicality of the matter. Will it sell? Will it actually change things relative to today? That's not what we're talking about when we're talking about life cycle design. Okay, is that clear? If so, then I want to share with you a tool for life cycle design called Simapro. How many people have heard of Simapro? Nice. How many people have used Simapro? What percentage is this?
15.
I thought you were going to say like 18.2, something like that. So about 15%. So this is a tool that, and I know you're thrilled to be thinking about the next homework assignment. But there is one coming where you will use Simapro, and we think you're going to like this, but we can't be sure. So I want to spend the rest of the period today just talking about Simapro some, because only about 18.3% of you have used Simapro before. So it's a little quirky, and I just want to get you used to looking at it. I mean, there's no substitute for playing with it. And I kicked around the idea of playing with it in front of you, but I don't think it's as effective as the sort of screenshots. So we'll talk about it just in the screenshot format. It's set up like an LCA, so in that sense it's intuitive. But when you get into it a little bit, it's a little bit quirky. So you'll see that in a minute. And then the question is, okay, well, how do you navigate? Where do you get data? And then I have some extra slides I'm not going to go over, but if you look at the when you go online and you grab the PDF, you'll see that there's some extra slides should you ever want to enter data into Simapro. And I should acknowledge Colin McMillan is a PhD graduate. He took 589 in fall '06, and for a term project he did some slides. He also did a homework assignment. You're doing a different homework assignment, but Colin was a great student, and he's actually an LCA practitioner now, so he's doing well. So okay, let's take a look. So what is Simapro? It is marketed by, it's widely used. It's probably the most used by this group called the Product Ecology Consultants. And the reason I'm not big on Simapro per se, but we have it here. That's why we're teaching this one to you. So you can use it, you can get used to it, and get some experience practicing with it. So we have a nice educational license on Kane, and your next assignment you're going to look at the design of a corkscrew. Okay, so hopefully a simple product that we can all kind of get into and start thinking about some of the issues of life cycle design. So it's really two or three things. One, it is a source of data. Now, Colin called this a large amount of data, and it is a large amount of data. When you think about how much data you need, I mean, think about, like, this is a general tool for all of engineering. Like, it's really limited in that sense. I mean, there are a lot of materials there, but when you go and try to use it for your product, especially the educational version, there may be hundreds of materials and other processes there, but it's not enough. It's not sufficient. So there is a large amount of data, and it's not necessarily publicly available. So that is a strength. It speeds the calculations. You can build models with it fairly easily, and you can tie it to the impact assessment metrics, by snapping your fingers, basically. So it's convenient that way. So you can, build large, complicated products. If you need a truck to make a truck, and you don't want to program that into Excel, this will take care of the loops for you. So it's nice that way. And it gets you thinking not only about the data and the structure of your product, but also about the functional unit. There are convenient ways to input that into your life cycle and what have you. Okay, so it is organized. This is a screenshot of Simapro, organized by life cycle stages. So here's your goal and scope, and here's your inventory. Here's the impact assessment and the interpretation. And we'll just say a few more about these. Okay, so your description, as you might guess, this is your goal of your project. You put your functional unit in. You can put other comments there, and you're going to see comment boxes as we look at screenshots for the same coffee maker we just went through. When you see those screenshots, you see comments. There's a nice way to make clear what some of the embedded assumptions are. They also have opportunities to input with the data these data quality indicators. So we talked about what a good LCA is, and a good LCA is using representative data. So you can make comments about what maybe it's a machining process. Well, what machining process? Not just a general. Is it drilling? Is it milling? You've got opportunities to talk about what the data is in that field. That's called data quality. And especially if you're using somebody else's data, which you're almost always doing, then you want to know, from when was that data collected, where, what were the system boundaries, what allocation methods, all things we talked about early on in the class. Okay, and you can use that to evaluate how appropriate the data is. So 2 statements you already know. Here's the first one. You want to use the most current data in the same geographic area. You want the data to be representative, and you want to completely document that. Okay, and Simapro gives you the opportunity to do that. Okay, so goal, scope, and definition. Hopefully no surprise here. It's obviously based on LCA, so this is familiar to you. There are basically three different things that are called, we call building blocks. So there are three ideas that you need to understand with Simapro. And they're flows, states, and things. Okay, so let's start with flows and states, and then we'll talk about things. So flows are almost always environmental flows. So this is emissions, typically. So they could be emissions to the air, to the water, to the soil. They may be material emissions, solid waste. It may be consumption or use of natural resources. So just about everybody uses Simapro to track environmental flows. Right? They have the ability, because they know about sustainability too, to track economic flows as well as social flows. But practically nobody does that. Now, you can think of a product being an economic flow, but you can also think about a product as a system, right? And a system that's basically a transformation from inputs to outputs. So, not often you're inputting money into Simapro, and almost never. I've never seen an example of people thinking about social flows. And we're not talking about flows of people here. What we're talking about are the association of job creation with a particular process. It would be a good example of that, or other aspects that might involve justice, right? This is a hard thing, and so they just sort of allow you to create those flows. If you're creative enough, this allows Simapro to be flexible into the future. This is obviously an area of research, as we've talked about. Okay, so processes or flows are one concept used in Simapro. The second are product stages. I like to call them states. So for people who are familiar with states and flows, this kind of resonates a bit. So a state is, it could be an assembled set of components. It can be the life cycle. You could define a life cycle of a coffee maker, and that's a state. You could talk about disposal scenarios. You could talk about reuse, disassembly. You could talk about manufacturing. Talk about transportation. So these would be states. And there are flows that may be associated with the states, obviously. Okay, so there's flows or states, and then there's two kinds of things. Again, I should have labeled that here, and I didn't. Actually forgot. So there are two kinds of things. One are substances. Substances come from nature, and inputs come from the market or the technosphere, right? Engineered stuff, people were involved. So substances are, we're going to use calcium carbonate from the earth or bauxite. Substances. An input might be something from another process. So maybe I, mined copper. Now I have copper that's engineered copper, and I'm going to use that. That would be an input. Okay. So copper ore might be a substance where the engineered copper alloy is an input. Okay, making sense? Go ahead, Steve. That would be an input because people touched it. So if we talk about steel, steel ultimately comes from taconite, some kind of ore. That's a substance. And it gets purified and then ends up as iron pellets and then it's an ingot eventually. Okay, makes sense now? We've got our flows, we've got our states, we've got our things, which are substances and inputs, and just the difference is whether they come from nature or not. Okay? So just to make it crystal clear, we hope, we could talk about substances, again, being the inputs from nature. It can also be emissions to nature. That's on the bottom level here. In the middle, you may have exchanges among the technosphere. You may also have direct inputs from nature into the technosphere here. These are processes. And then you've got the product stages that use inputs, and all together they define the life cycle. This is the basic organization. I don't think it's very intuitive, honestly, but we're stuck with it. But I haven't programmed one of these, so we're going to use what they got. Okay, making sense? This is just an example then. So, oh, that was fun. All right, so, okay, I did that one. All right, so this was limestone maybe coming into a process that's actually mined now. You might use limestone to make a coal-fired power plant, and you might use electricity to mine limestone, right? So these are just an example of exchanges. And that limestone might ultimately be used in fiberglass. You're going to need some electricity there. And ultimately, this is the life cycle of a residential home. Okay, so these are examples. Okay, and probably incomplete when I stop and think about it. Okay. So thinking about the difference between systems and unit processes now, I already in passing defined this. So a system's a black box. Right, we talk about a box model. So if I use the restaurant example that Lisa and I were talking about earlier, I just think of this coffee maker. I put water and electricity into it, and coffee filters into it, and I get coffee out, and I get waste coffee grounds. I'm not looking at anything going on inside the coffee maker. Or more generally, I may be doing a life cycle assessment on somebody's eating habits. And so I'm looking at where they might eat. They may drink coffee. That coffee comes from a coffee maker. I'm unlikely to actually dive into the unit processes of a coffee maker like we were talking about before. So a system is basically just when you have inputs and outputs, and it's very opaque. Ideally what we want are all the unit processes. And the more unit processes we have, then that's nice because we can use unit processes as building blocks in other places. So the idea in a good database or a good useful software like Simapro is to try to have as few black boxes as possible. But they have black boxes. So if you go to a particular alloy of steel, it's probably going to be a black box. But for general steel, they might have all the unit processes laid out. So the idea is just to define those two things, the idea of a system in Simapro, which is a black box, and the unit processes are sort of your finest resolved unit there. Okay, and this just shows what it looks like in Simapro now, where we've got on the left side here a system where all you're seeing here are the inputs from nature and the outputs to nature. So these are emissions to air down here, and these are inputs from nature. So these are iron pellets, and we've got some ore going on here, and then we've got emissions to air. Now if we were to include unit processes, right, you see here you're going to need some electricity, you're going to need some rail transportation, a furnace, and even this is not going to include all of the unit processes involved. Okay, so that's the difference between a system and unit processes here. Unit processes are listed out. Making sense? So once you have building blocks, then you can start to put them together. And that's one of the strengths of Simapro, where you can just sort of grab blocks and throw them into your system. You can define your product stages however you'd like. Assemblies are defined from cradle to gate. How many people are familiar with a phrase like cradle to gate? Okay, not many. Who can give us a definition of cradle to gate? Who's willing to? I'll go ahead,
It would be like the life cycle from the procurement of the raw materials to when it leaves the factory. So it doesn't include use or disposal phase.
Exactly. So the gate, you can think of that as just leaving the factory. I think Andy said it very well. And after that point, use and disposal, they're going to be treated separately, right? So we've got end-of-life scenarios, and then you've got the use phase embedded with the life cycle. So you just treating these assemblies, if we're talking about the coffee maker, basically it's the point at which you've produced and packaged the coffee maker. At that point, you've got this assembled thing. Now it's going out. Okay, or more likely, the way you would do that is you would just assemble the coffee maker, treat the packaging as an association with the life cycle. So there is an opportunity in Simapro to define your associated your associated products, or it could even be associated assemblies. Okay, so just looking at how you might assemble these building blocks. Here's you've got an opportunity in the product stages. You've got your assemblies, cradle to gate here. You've got sub-assemblies, and then the production of use phase products. So if it's water for your coffee maker, then that would show up. You define your life cycle as, you can have alternative scenarios, and then how you're using the products, how much water. So this might be the production of the water, and this might define how much water you're using. So you've got your use phase, same goes for electricity. You've got your disposal scenario, where the question is it going to municipal waste? Is it being taken back? And once you define, maybe it is being taken back, then you might have operations such as disassembly. You might even have some reuse. So these are sort of embedded options within Simapro. So now looking at what an assembly might look like inside of Simapro. Here we're looking at the coffee pot. We're looking at the materials now. Here's the polypropylene handle. Here is the glass. We're looking at the masses here. And then comments on the right-hand side. This is not complete. These are just screenshots of a few. So here are processes now. So we're talking about the coffee pot. It's not just materials. It is the processing of those materials. So the handle is going to be injection molded, and you're going to have heat going into a furnace to form the glass pot. Okay, so that's what it might look like. Then now assembling into the coffee maker itself. We could talk about the process that is electricity consumption in the use phase. We can think about the waste disposal scenario that lays on top, so we're going to treat this as household waste. We have to think about additional life cycles. This is what I was talking about before. So the coffee filter is an additional life cycle. And so here's your 3,650 coffee filters that went into the life cycle, the packaging. That is an additional life cycle on top. So you've got your assembly. Once the assembly is made, you've now kicked into play, and Simapro does this all behind the scenes. Once you define the assembly, that means you've got the materials, you've got the manufacturing processes, and you've assembled them. You've got the assembly, so the assembly has a use phase, it has an end of life, and it has additional life cycles with it. Okay, making sense? Go ahead, Vinny.
What's the distribution tab there?
Hold off on the distribution tab.
Okay.
That's a Monte Carlo analysis, and I'm trying to get there today. We'll see. So just to say a little bit more about the waste. So when you define a material, you have to define the waste type. So you're not really going to be defining materials, so that's going to be less of interest to you. But at the bottom here, here is a specification on waste. So this is the household waste that the coffee maker would have been associated with. So that household waste is a specific process. If this scenario for household waste, this is demo number 7, if that's not a good scenario for your household waste, then you create a process of your own. And so maybe that's going to be scenario or demo number 8. Right? And but here, that household waste is associated with a certain percentage of the paper being recycled. So of 100% of paper that would be in the product, if you associate your life cycle with this household waste, then 36% of the paper is going to be recycled. And the rest of it is going to be municipal waste, landfill. Okay? So household waste is not all municipally landfilled. Some of that household waste gets recycled, and 36% of the paper gets recycled, and 78% of the glass gets recycled, and 36% of the cardboard gets recycled. And I know for sure these are not U.S. numbers, right? Without trying to quote what I believe those numbers to be, they're quite different, actually. Okay. And then this is at the bottom here what happens in the lead. So this is very hard coded. Okay, it may look arbitrary to you, but the fact that there is an end of life stage and that recycling happens and reuse happens and disassembly happens, it's all sort of hard coded into Simapro here. Okay, so now we're looking at the municipal waste, and even with the municipal waste, once something goes to potentially a landfill, there may still be some recycling processes. So you might get some steel recycling, some aluminum recycling. And these are all part of what these folks who put this software together in the Netherlands, what they decided. And if you're looking at these numbers saying, well, I don't want to use those numbers, I want to change them, then you can define your own scenario. Right? And you can associate your life cycle with those processes. That's what we're talking about. We're not necessarily going to ask you to do that in the homework, but I do want to give you sort of a comprehensive view of what the software can do. So you might use it later. What is not ending up as recycled material is either going to end up in a landfill or it's going to be incinerated. Those are processes too, right? So being able to link into your processes that exist is very handy. Right? Versus going out, looking up the studies, inputting all the numbers with hundreds of substances into Excel yourself. So it's a very convenient software from that perspective. Okay. So this is now looking at a disposal scenario for a coffee maker. This is your aluminum version. So this is the one with the insulated carafe. And basically, there's a disposal scenario by which the assembly is transported, and some fraction of it becomes municipal waste, some fraction of it's disassembled, some fraction of it's reused. Okay, so you can define that, and then you can say, okay, well, what is that disassembly going to be? So 49% of the disposal goes to disassembly. And I know we have some friends from abroad here thinking, well, only 49% is recycled. That's probably a high number for here. But we've got that assembly model that is part of that disassembly is going to be transported somewhere else. There's going to be some electricity used to disassemble the product. And then for the aluminum there, in this case, 95% of that aluminum is actually going to be disposed, which might be a little bit surprising. But there's a note over here that says, although the aluminum parts are collected, the disposal scenario refers to the aluminum parts. So in other words, you've got aluminum parts that have already been separated. So this is the extra aluminum, and it turns out to be not a lot. So basically, it's that aluminum that's hard to get. So you can get down to that level of, okay, that subassembly is hard to get. It's aluminum, and we're only going to get about 5% of that. Right, so very nested and somewhat complex. Okay, but you get the idea. You've got substances, you've got processes, you've got product stages. This is just at the end of life, and this is some of the interactions that lead to the product stages. Okay, so talking is cheap. You can get a sense only by playing with it. That's why we hope we've put together a simple design example for you where you're actually going to use some of this. Now, to Vineet's question, what are those tabs? So basically, once you've put all those unit processes together, you've defined your assemblies, you've defined your life cycle, you've defined your disposal routes, so your end-of-life routes, then you put all that together, and then you want to analyze it. So there are different terms used in Simapro. There's network, there's tree, there's analyze, compare. And then the question Vineet asked, what was the histogram? That's your uncertainty analysis, it's Monte Carlo there. So he's talking a little bit about it. If we're looking at just the distribution of the coffee maker to a warehouse that might involve rail, that rail transport involves fuel, it involves some electricity, it involves some infrastructure beyond it. This may be something that you want to just go grab. I need to move my coffee maker from point A to point B. I'm doing that by rail, so I'm going to go into Simapro. I'm going to grab that process, and you're not going to look at the unit processes that are under this, right? But you can by clicking this is the network button. The difference between a network and a tree, you know, that you need fuel to run a train, but you also need a train to get fuel, right? So it's the same thing. You need a truck to make a truck. That's what a loop is. And that sort of iterative iteration, if you will, or feedback gets automatically taken care of for you inside the software. But what it also does is it makes it messy to look at. So if you click the tree button, it'll get rid of the loops. And it'll just look at it from lowest to highest assembly, and then assemblies of other unit processes. Now these red bars, these are units of eco-indicator points. And you're looking, you can basically at a glance figure out where most of them are. So you could figure out, okay, well this one seems to be important and this one doesn't, just by looking at it. Okay, so that's networks and trees. You can analyze the data just by clicking the calculation setup. You hit the Analyze button, and you're going to get inventory results for all the substances. You also get all the emissions. It breaks them down by the life cycle stage, so the waste stage, or the coffee maker stage, or the packaging stage, or the use phase of the product itself, electricity. And you can define what those stages are. Okay? And it all kind of comes out in the wash nicely. Okay? There's impact assessment. That's what the other buttons do. So classification, characterization, valuation, we've already talked about. There's also normalization. If you take the characterized results and you look at which processes contribute by percentage to the total, like we did with the unused pharmaceuticals case study, we looked at, okay, here are 100% of the global warming impacts, and we can attribute to each process. That's what's called normalization here. Okay, so just taking a quick look. ISO standards only require these two, as we've talked about. You know, that valuation step is not required, and nor is the normalization step. Okay. Eco-indicator 99 is one method. There are other methods we're not going to talk about here that are in the software, like EcoPoints and Impact 2002. Midpoint methods, we talked about Tracy just a little bit in passing. There's also the CML. And you can specify. Okay, so you can look at, if we're looking at Eco-indicator 99, which we've talked about a few times, you know, we can then look at the damage model and actually get to a point where we're actually calculating impacts. And we've discouraged you from doing that. What might be interesting is looking at multiple damage models. So look at CML, you look at impact, look at midpoint indicators, look at endpoint indicators. And if they're all sort of pointing you in the same direction, then you know there's probably some truth underlying that. Looking at all of them, there's nothing stopping you from doing that. And you can maybe, if you're using this to generate design concepts, then you know, knowing that there might be a water issue that comes out from one method to get you to think about water, or Eco-indicator 99 is a little bit more biased in climate, you know, that it's helpful to look at all of them.